Hello, my name is Badjo Tete, and this is my final project report for my HAP 780 Data Mining and Healthcare course at George Mason University. In the following discussion, we will delve into my report centered on the precision forecasting of malaria epidemics, integrating meteorological patterns, urbanization, and child mortality rate. In this presentation, I will provide a comprehensive overview of my research on precision forecasting of malaria epidemics, which integrates meteorological patterns, urbanization, and child mortality rate. I will delve into the background, discuss relevant literature, present the data collected, outline the methodology employed, showcase the analysis results, draw conclusions, and acknowledge the study's limitations. This holistic approach aims to enhance our understanding of the complex factors influencing malaria outbreaks and contributing to more accurate epidemic predictions. Malaria persists as a critical challenge in sub-Saharan Africa, sustained by favorable conditions for Anopheles mosquitoes. Vulnerable populations, particularly children under 5 and pregnant women, faced heightened susceptibility. The epidemic is intensified by factors such as poverty, limited healthcare access, and inadequate infrastructure. Despite migration efforts, challenges include drug resistance, scarce resources, and climate changes impede effective malaria control. Furthermore, the severity of malaria varies significantly between rural and urban areas in sub-Saharan Africa. This literature review highlights the critical impact of meteorological factors on the life cycle of Anopheles mosquitoes and Plasmodium parasites, influencing malaria transmission. Diverse machine learning algorithms, as evident in the report Prediction of Malaria Incidence using Climate Variability and Machine Learning, enhance predictive accuracy in capturing the intricate climate-malaria relationship. Urban growth discussed in the report Urbanization, Malaria Transmission, and Disease Burden in Africa alters malaria dynamics, necessitating target interventions. The report Malaria, Infection, Disease, and Mortality Among Children and Adults on the Coast of Kenya emphasizes the heightened risk for children aged 6 months to 4 years, guiding interventions and refining predictions. This slide provides a snapshot of our precision forecasting of malaria epidemic study, featuring a sample of the dataset used for the precision forecasting model and a map illustrating malaria prevalence in sub-Saharan African countries. The datasets sourced are diverse, including meteorological data, urbanization statistics, child mortality rate, and reported malaria cases from the World Bank. The map utilizes gradient shading to highlight varying incident levels, aiding in the identification of hotspot regions. This emphasizes the importance of our precision forecasting model for early detection and targeted interventions in high-risk areas. The visual representation of precipitation versus malaria incident in sub-Saharan Africa highlights a clear correlation between higher precipitation levels and increased malaria cases. This underscores the crucial influence of meteorological patterns, particularly precipitation, on malaria prevalence in the region. Meanwhile, the graph illustrates urbanization versus malaria incident over time, reveals an intriguing inverse correlation, suggesting that as urbanization increases, malaria trends decrease. However, this trend warrants careful interpretation due to the complex impact of urbanization on malaria dynamics, as evidenced by challenges such as increased population density, sanitation issues, and healthcare access disparities. The observed rise in malaria cases between 2019 and 2020 emphasize the need for nuanced public health strategies that account for the evolving challenges imposed by urbanization in malaria regions. The application of the interquartile range, also known as IQR, initially confirmed the absence of outliers in the dataset. Subsequently, the k-means clustering technique, guided by the elbow method, which determines the optimal cluster count, which in this case is 3 as shown in the graph, revealed distinct clusters in the dataset. The k-means clustering results highlight the distribution of instances across clusters. Remarkably, the absence of outliers in the k-means clustering process aligns with the finding of the IQR assessment, emphasizing the consistency of results. In evaluating the random forest method on the training set, the model demonstrates strong performance with a correlation coefficient of 0.9978, reflecting a robust positive correlation between predictive and actual values. The mean absolute error, also known as MAE, of 7.5975 and root mean squared error, also known as RMSE, of 10.7738, underscore the model's accuracy in capturing variability within the training dataset. Similarly, in the test split, the model maintains solid predictive performance with a correlation coefficient of 0.9649 and relatively low MAE and RMSE. Cross-validation results reinforce the model's robustness and consistent accuracy across different subsets of the training dataset, substantiating its potential for practical application in precision forecasting for malaria incident in sub-Saharan Africa. Overall, the random forest method applied to a diverse dataset consistently demonstrates strong performance. Precise predictions were evident in the training set with a robust correlation of 0.997. The model's accuracy persisted in the test split featuring a correlation of 0.9649 and low error. Tenfold cross-validation affirmed high accuracy. These results collectively validate the reliability and effectiveness of random forests in precision forecasting for malaria incidents across varied datasets. In conclusion, the precision model leveraging the random forest method has proven highly effective in predicting malaria incidences in sub-Saharan Africa. The model's consistently high correlation and low errors affirm its accuracy, offering valuable insight for proactive public health strategies. The integration of various factors in the model provides a holistic approach to understanding the complexity of malaria dynamics. Despite promising outcomes, limitations include limited data availability, variability in data collection practices, resource constraints, and potential impact of data quality on models' performance. Not all African nations were included due to challenges in comprehensive dataset sourcing affecting generalizability. Addressing these constraints requires improved data infrastructure, standardization, and accessibility. Caution in interpreting findings is advised, emphasizing the need for collaborative efforts, data sharing agreements, and investments in data infrastructure to enhance future precision forecasting models in the context of African health research. These are my citations. Thank you.